Good day everyone. Assalamu alaikum. I am honored to present our paper at the 2026 IEEE Second International Conference on Quantum Photonics, Artificial Intelligence and Networking, QPAN 2026. The paper ID is 6605 and the title of our work is XAI-Powered Vision, Making CNN Malware Classifiers Transparent for Cybersecurity Frontlines. This research has been conducted by Shaukat Hussain, Turju Talukdar, and MD Ajat Hussain Sir from the Department of Electronics and Telecommunication Engineering, Chittagong University of Engineering and Technology. In this presentation, I, Shaukat Hussain, will demonstrate how we integrate explainable artificial intelligence with a CNN-based malware classifier to address one of the most critical challenges in cybersecurity AI systems, the black box opacity problem. We decided to work on this topic because modern cybersecurity increasingly relies on deep learning for malware detection. However, while CNNs achieve high accuracy, they operate as opaque black box systems. In security operations centers, analysts require forensic-level interpretability, not just predictions. To bridge this gap, we trained a 3.3 million parameter CNN on the Malimg dataset using 128 by 128 grayscale PE images across 25 Windows malware families. We then applied Saliency Mapping to visualize discriminative regions corresponding to PE structures such as .text and .data sections. This transforms a detect-only model into an evidence-backed forensic tool. The objectives of this work are, first, to classify malware families using CNN-based image representations. Second, to achieve high-fidelity classification across 25 Malimg families. Third, to integrate Saliency Mapping for pixel-level interpretability. Fourth, to mitigate the black box limitation of deep learning. And finally, to assist SOC analysts with visual, explainable forensic evidence. Let's now discuss about the methodological approach we have used. First, datasets and preprocessing. We use 9339 grayscale images derived from Windows PE binaries in the Malimg dataset. Each binary is converted into an 8-bit unsigned integer matrix and resized to 128 by 128. The dataset includes 25 malware families. However, Malimg presents severe class imbalance. For example, Alappe contains hundreds of samples, while families like skin trim are under precedent. To address this, we applied cost-sensitive learning by assigning class weights during training rather than oversampling. This ensures minority families are properly learned. We used an 80-20 train test split. The 20% test set was strictly held out for final evaluation. Training curve shows convergence by the 6th epoch. There is no divergence between training and validation accuracy, indicating minimal overfitting. This confirms the model learned generalized byte image representations rather than memorizing samples. Our proposed CNN consists of 3 convolutional blocks. First convolution, 32 filters, 3 into 3 kernel, captures low-level byte textures. Second convolution, 64 filters, extracts mid-level PE section boundaries. Third convolution, 128 filters, learns family-specific malware textures. Each convolution is followed by 2 into 2 max pooling. The feature maps are flattened into 25,088 units. A dense layer with 128 neurons and ReLU activation follows. We applied 0.3 dropout to reduce overfitting. The final softmax layer outputs probabilities across 25 malware families. The total parameter count is approximately 3.3 million, significantly smaller than standard architecture like ResNet 18. As from the result, we can see that the model achieved 97.4% test accuracy, 0.97 weighted F1 score. The confusion matrix shows near perfect diagonal alignment across 2 into 1 of 25 families. Minor confusion occurred in polymorphic families such as Suizo due to structural similarity. However, dominant families such as Alappe and Adealar achieved perfect F1 scores. This confirms strong generalization across malware genealogies. To address interpretability, we implemented vanilla gradient saliency using the CAPTAM framework. For each input image, a saliency map assay was generated. We computed average normalized saliency per PE section using equation 1 shown here. The results reveal that for families like ADLRC, the .data and zero padding regions contribute more strongly than the .text section. This indicates that structural artifacts beyond executable code significantly influence classification. Additionally, we analyzed misclassified samples. For example, in one case, incorrect predictions shifted focus from the .text section to the .data region. This forensic level insight allows SOC analysts to understand whether errors are caused by obfuscation, padding noise, or structural similarity. Unlike SHAP, which requires exponential perturbation, our gradient-based approach computes attribution in a single backward pass, approximately 35 times faster for 128 into 128 images. Thus, we achieve both interpretability and computational efficiency. So we can conclude that this work addresses the black box challenge in CNN malware classifiers through saliency-driven explainability. By linking pixel-level activations to PE structural regions, we converted opaque classifiers into transparent forensic decision tools. The framework reduces false positives caused by zero padding noise and enhances analysts' trust in AI systems. Future work will focus on adversarial robustness and deploying XAI-driven tried systems in distributed real-time SOC environments. Thank you for being with us and here in this presentation. Signing off here, Shaukat Hussain. Assalamu alaikum.